Well, thanks everyone for joining. Today we have the pleasure of welcoming Dario Azzimonti from the Dario Institute for Artificial Intelligence. And he's going to talk about his research on preference learning with Gaussian processes. Dario, the floor is yours.
Thank you, Victor, and thank you for having me today. I'd like to start, this talk. I know that by saying that I know that all of you do a lot of great work on Gaussian processes. So my main objective with this talk is maybe to show you a slightly different application that you might not have seen of using Gaussian processes. So what I will try to do is to be quite quick on the GP part, which I'm quite sure that most of you have already heard, and I will try to be more precise and maybe a bit longer on the preference learning part, which is this different application. So the works I present today are works that were done in collaboration with my co-authors. And so first of all, I want to emphasize that this is collaborative work. And my main co-author is Alessio who's now at Trinity College in Dublin. But also there is another Dario from my institute and Diego, who also helped us a lot with the code. If you are interested in what I'm going to talk about today, you can find a lot of what I'm going to talk about explained in a lot of details in this tutorial paper, which we just recently put on arXiv. This is kind of a tutorial paper, so it's quite long. However, it's a good starting point because it really puts everything it presents everything in an orderly fashion. And I think as opposed to the other references I will give throughout the talk, which were more research papers, so they might require a bit longer to get into what is the topic. So instead, I would suggest this is a good introduction. And if you want to play a bit with the code, we also have a Python implementation of all these methods with some notebooks as examples. Then you can find them here. So the Google search word is prefgp, but I don't know if I will send you also the slides in case all the slides have links. Okay, so the idea for today, again, is to present you preference learning and different ways of seeing preference learnings with, I would say, kind of 3 points of view. One which is object preferences, the other one which is label preferences, and the last one which is choices. And I will show you kind of what type of models you can use to learn from this type of data. So before I go into the details of the different models, maybe it's good to specify what I mean by preferences. So here the idea is that we have we have observed some type of user behavior, and this user has expressed his preferences in some way, okay? And examples where you could express these preferences are practical example. Well, for example, you're looking for buying a laptop. There you could make comparisons between different laptops, and you could have different ways of doing this comparison. And we will see that when you do pairwise comparison, so you take 2 laptops and you say, I prefer laptop A to laptop B, this is one type of data. And from this type of data, we can learn the user preferences with a Gaussian process. Another type of example that we will see in a little bit is how to, if we have different users and we want to suggest to an individual user is best gaming platform based on some features that we have observed. For example, how much time a user is playing a certain type of game, for example. And in that case, you can see already that this is slightly different because we don't have one single user, but we have many users. And would be better encoded with labeled preferences. Finally, a more general option for this instead is to learn from choices. And I will go into a bit more detail on that later. So yeah, so this is kind of a quick summary of what I'm going to say next. So the example of buying a laptop, there we have one user, and this user is expressing pairwise comparison between objects. So I am choosing a new laptop, and I'm comparing laptop A, laptop B, laptop A with laptop C, and so on. And the features are associated with the individual laptop, so with the items. The next one, the next kind of family of preference data is labeled preferences. And there instead, we have a group of users. So the features are associated with the individual user. And then we make, for example, pairwise comparison between labels associated with the object. So in this case, the labels in the example of the gaming platform will be which gaming platform. And then we will have individual features associated to each user. The last kind of type of data is a more general data, which is where users select items from a fixed set of options. So instead of giving me 2 laptops to compare from, I have 5 laptops, and then among those 5 laptops, I choose 3 laptops, for example. The third option kind of gives rise to more complicated problems when actually modeling this, because we don't have a fixed amount of items that we don't know how many items the user will choose. Okay, so just to be a bit more precise, since we are going to use this notion for throughout the talk, let me define what I mean by a preference mathematically. So a preference for me is, well, first of all, here I'm only considering strict preferences, and this is a binary relation where for 2 items, X and Y, I want these 2 properties, so that it is symmetric and that it is negatively transitive. So, well, symmetry, I think, is quite self-explanatory. For the negative transitive, the idea is that we kind of want to avoid the possibility of having cycles, okay? So when we have a preference, one thing we can do is, if this preference satisfies these 2 properties, one thing we can do is we can represent it via utility functions. So this means that I can create a function u, which is defined on the set X, which is where I create my pairwise preferences, pairwise comparisons. And this function u tells me that the function is greater. So this is a real valued function, and this real valued function is greater in X takes greater value in X than in Y, if and only if X is preferred to Y. And one important thing here is that this representation is not unique. Because what counts here is really the comparison between the values, so which value is higher than the other one. So as long as I can modify this relationship with any increasing function g, that you can see here, and this is still going to be true. This is an important point to make, because then when we need to learn this function u, we will need to take this into account. Okay, once you have kind of these tools, then you can start to create models to learn this latent utility U. Okay, so imagine you are in a situation where we have collected some data, you have collected some preferences, you only see the preferences, you don't see the function U, but you can still create a model to try to learn U. Historically, these models have been mostly based on generalized linear models. There has been also some support vector machines on this. However, the focus of this talk is on Gaussian process-based models. In the end, the main reason why also in the literature we have moved more towards Gaussian processes is because then they allow us to do things like Bayesian optimization. So they have a practical use. So we pay the price of estimating also an uncertainty, but then we can use this uncertainty inside some more complicated pipelines like Bayesian optimization. So here I have 2 slides on Gaussian processes, but I'm going to be very quick here. Well, this is kind of the probability definition of a Gaussian process, but maybe what's more interesting for us is how to use a Gaussian process inside a model, so how to learn an unknown function with a Gaussian process. And the idea is to use this method. This is a Bayesian method, a non-parametric method that allows us to fit unknown functions. So we want to fit this unknown function. We start with prior on the functions. In this case, I'm showing you the samples from Gaussian process. So these are 1D samples of a GP, which were drawn with an RBF kernel. We observed the values. So this is a regression example. So here we have observed values of the unknown function with some noise, very little noise in this case. And so our observation, so what we want to find is the dotted line here, the dashed line here, and our observations are the crosses. And with the way we model this is with a likelihood, which links the values that we observed to the latent function values u. And then we have a prior on we have a, sorry, this should be f. Then we have a prior on the function f. We have a likelihood. And with Bayes' theorem, we can compute the posterior. So all of this is nice and works very well in the regression case. What we will see in the remainder of the talk is what happens, how do we link observations which are not values of the function with the latent function values? So how do we do this in the case of preference observations? So again, I don't think I really need to convince you on maybe why use Gaussian processes, but those are a few points which are good points of Gaussian processes. Clearly, I'm just emphasizing the good ones. There are also bad ones, which you're probably also aware. The fact that, for example, yes, the posterior is analytical, but if you actually use this formula, then and you have a lot of data, then this is most of the time is not feasible. But we have solutions also for that. So what I'm going to focus today on is not how to solve those issues, but how to generate these models when we do not observe outputs that are the values of the latent function, but when we observe preferences. So this pairwise, first of initially pairwise comparison, and then we will make it a bit more complicated. Okay, just to go back to kind of what we have in preference learning is what we observe is simply that for an item, for the green item, we prefer the green item to the red item. Associated to the green item, we have a set of features, which is this vector x. And associated with the red item, we have another set of features, which is this other vector xjs. The idea is that we want to learn this underlying hidden function u, but what we observe is simply that the green is, so what we observe and what we assume is that the value of the latent function at the green point is greater than the value of the latent function at the red point. So the way we proceed with this is we create a likelihood that links the observed preferences with the latent function values. And the idea here is very simple. So we start with a model which we call the consistent object preferences. So this is not historically the first model that was created, but in my opinion is probably the simplest one. So it's worth starting from this one as an explanation. So here the idea is I'm assuming that my user will give me consistent preferences, which is clearly a strong assumption and most of the time not true. So then we will see how to handle this issue. But in this case, what we can say is we can relate my latent function values with my preferences by pretty much using the preferences to create this matrix W here. Now, this matrix W here, what it's simply doing is saying, okay, I've observed that for example, this item here. So if we just look at the blue couple here, xi1, here, the value of my function u there should be higher than the value of my function u at xji. Okay. So then I'm simply encoding this constraint that is saying that the function at so probably you can also see it here. So the function at xis minus the function at xij is greater than 0. So I'm doing something extremely simple here. I'm just encoding constraints inside this likelihood. I mean, here, I'm just showing it because this is a sequence. This is in the end a product of indicator functions. So one for each of the observations. And here I'm just showing the different indicator functions. Once we have this likelihood, then we can compute the posterior. Our posterior in this case is simply going to be, since we have that the prior is a GP, we have this type of likelihood, we are doing a product. So then pretty much what we are doing is we are doing a truncated normal where we are including the constraints of which are given by the preferences. Now, this W here, well, yeah, is if you're curious, well, it's simply a matrix which contains all the preferences where we put the 1 and the -1 in the appropriate locations. Okay, once we have this posterior, then we can compute the predictive posterior. You can already see here probably that if you need to do this type of integral, this is quite complicated because you have this truncated normal here in the middle. This is not the only issue with this type of model, and actually it's not even the main issue in my opinion, because the problem with this type of model is that we are assuming that all the preferences that we are observing are consistent. However, it happens a lot in practice that the preferences are not consistent. What do I mean by not consistent preferences? I'm looking, for example, at these two couples, so the red one and the green one. First, the user is telling me that A is preferred to B, and then for 2 points which are very, very close, the user is telling me that D is better than C. So since we want to have one unique underlying function, if we don't allow for errors in the user preferences, then this is not going to be consistent. So one way to handle this is instead of using indicator functions as likelihood is to use soft indicator, so to use instead the CDF of a Gaussian. So this is pretty much this is exactly what we are doing here. So this was actually the first, to my knowledge at least, the first GP model with preference learning that was introduced in 2005. And at the time, the idea is, okay, we have a prior, we have a likelihood, let's compute the posterior. At the time, they were doing it with a Laplace approximation. What we did instead recently is we had a look at what is the actual shape of this posterior distribution. And I mean, one thing you can always do is compute it with Monte Carlo. And if you do that, you will see that while the Laplace, and here I'm also plotting the AP approximation of our posterior in one particular example, while they are well, clearly Gaussian because they are Gaussian approximations, the actual posterior is not Gaussian, which is not really surprising. But what is more interesting maybe is that this is a skewed distribution. And we have a way of actually handling skewness. And so what we propose to do instead is to actually compute the parameter of the skewness, and there are analytical formula for this, and obtain an analytical posterior distribution. So this is what kind of the structure of this SkewGPs was, why we introduced the structure of SkewGPs. And maybe just to give you an intuition of what are those parameters of skewness that we are introducing here. Here is an example where we have a vector. In this case, this is a bivariate skew normal, and what is the impact of the individual parameters. In summary, what this type of structure does, don't focus too much on the equation here, but maybe just on the parameters here. So we have location, a scale parameter, so covariance, and then we have these three parameters here which handle skewness. We need three parameters because we also want to have the flexibility of having different direction of skewness. So in this case here, we have one direction of skewness, so we are taking the bivariate Gaussian, and we are kind of skewing it along this direction. In this case, we're skewing it along two directions. And you can see that by using the appropriate parameters, we can control the skewness. So this is for a vector. Actually, this is for a bivariate vector, but then we can generalize this to a stochastic process. So this is what we call the SkewGP. And in the end, this is is the equivalent stochastic process that we obtain when you have marginal distributions, finite marginal distributions, which are skew normal. So we have all this type of parameterization, which, to be honest, is interesting, but is not that interesting. What's more interesting is that if you actually take as a prior a GP, so simple GP, and now here I'm using directly the notation of the SkewGP, so with a mean function C and covariance matrix, covariance kernel omega, then if you have the likelihood that we showed before, so the likelihood with the probit, we can compute the posterior distribution in an analytical form, and this is a skew normal with these parameters here. So we have well, an analytical formulation for these parameters, which is quite nice because it allows us to kind of reduce a bit the computational complexity of then computing the predictive posterior. Because once we have this posterior distribution parameters, then we still need to do some sampling there because we need when we compute the predictive posterior, we still need to do some sampling. But we have, well, first of all, rejection-free sampling method, and then we only need to do the truncated normal part only once instead of having it to do all the time inside that integral I showed before. So, okay, so this is the this is kind of one force model for object preferences. what I have here is one example, which maybe I will skip, where we apply this to the choice of transportation mode. And then maybe I will show you directly the label preferences and the choices. Before I move on to that, just a quick note on this. So for object preferences, I've showed you two kind of models. The first one, which is the coherent preference model, which was the one based on which has a likelihood, which was the product of indicators. And for that one, with the fact that you are assuming that there are no user error, I would say this is not extremely practical. Instead, the second model was the erroneous preference model, where we have a probit likelihood instead. And we showed also that there is a way to compute analytically the posterior parameter of the SQGP. If you want to see more models about object preferences, we have still a couple of more in this tutorial, which kind of tackle a couple of different issues that you might have with object preferences. So a different way of encoding preferences instead could be label preferences. So here the kind of example to keep in mind is you have several users for which you have collected some data, and this data could be preferences or ranking among a finite number of labels. So the example I was mentioning before here is a bit more realized. So here you have Game Boy, PC, PlayStation, PS Portable, and Xbox as a type of gaming platform. And for each, in this case, they were students, it was collected what is their ranking among these options. And then for each user, we have some features which are associated to the subject, to the user. Okay. So in this case, we have to do the modeling in a slightly different way because we don't have any more the pairwise comparisons. But what we have instead is an ordering. So for ordering, we can look into kind of what are distributions on permutations. So the idea here is that if we have an ordering, in the end, this is a permutation of my labels. And what I can do is I can assign, given some score variables, I can assign a certain probability to each of those permutations. This is done with this Plackett-Luce distribution. And what we will do next is we will, instead of using score variables here, this will be our vector of latent functions, which will allow us then to learn the different user rankings. So the idea here is, okay, so for each, so let's assume that we have the utility function. For now we have a vector of utility function, and we will learn this vector of utility function with a multi-output model. The way we link our multi-output model with the preferences is by assigning to each of the rankings, so to each of the permutation, a certain probability with this likelihood. So this likelihood is the Plackett-Luce distribution. So the modeling part itself then is relatively simple. So what we assume that at least initially is to have independent GPs for each utility function. And we use the same kernel for each utility, but with different type of parameters. In order to compute the posterior, we use directly variational Bayes. So in this case, we don't have an analytical formulation. We weren't able to kind of do any type of Raoul equalization, where we find analytically at least part of the parameters. We simply resorted to standard variational Bayes approximation. In the end, what we are fitting here is multi-output GP with this likelihood, the Placet-Luce model. The example I was mentioning before about the different ranking of gaming platform is some data that was collected in 2012. And here I just want to show you, just to give you an idea of just to be clear about what is the difference between the label and the object preference. So here we know the feature of the student. So we know the age, we know the platform that the student owns, we know average number of hours. And we have collected some of these rankings. So, for example, this is one type of ranking, which is, this. So for this particular individual, this is the ranking that was expressed, and those are the features of the individual. In this case, what we did, since we already know that we have we already know how many labels we have, because we have rankings that are given. Then we can fit, we can fix the dimension of our multi-output GP to 6. We have our data set, and we use this Placet-Luce likelihood. Just to give you an idea of what a result look like. So in this case, we have a student, an example of prediction. So we have a student with this type of features. And what we will obtain is a posterior distribution for each one of the latent utilities. And in the end, in this case, we will choose the one with the highest mean, which I think is the PC, even if, for example, here we can see that there is a high uncertainty. So one good point about this type of models is, as always, that you can maybe do something smarter than, for example, choosing the posterior mean. You can adjust by including the uncertainty. For example, this is something you would do inside maybe a Bayesian optimization pipeline. So in this tutorial, we have a few more of these models. So you could also have label preferences with paired comparisons, for example, which is something I haven't showed, but imagine instead of having a ranking, you have simply a paired comparison, but then this paired comparison depends on the user that you are observing. You can encode label preferences with rankings in a slightly different way with the Thurston model. So the Placet-Luce is usually more flexible. However, in certain scenarios, this is also a model you could use. Overall, all of these models in general, at least as far as we know, they do require a variation. They do require some type of approximation, and we have seen that a variational approximation works better than other types of approximations. So in particular, Laplace for certain models, we can actually show that it cannot work. So that's an example of something not to use. Okay, I have probably another few minutes, so maybe I want to just show you the last type of data. So these choices. Maybe before I move on to the last part Are there because I again I don't see you, so I don't know if there are any questions lingering. Okay. Okay. So I guess I will move on. Okay. So the last type of data is, and here I'm using a lot of emojis just to make the explanation a bit lighter, is with data which is related to user choices. So the reason why I'm using this name is because those choices are actually more general. Those are generic choices and not, for example, pairwise label or pairwise or labeled preferences. So the idea here is that each user is given a certain set, which is a finite set of items. And among those items, what we observe is a set of choices, okay? So for each, so for example, here we have a set A, in this case with 2 items, okay? And then the user is choosing just 1 item. In general, this could be, well, A could be more than 2, and C of A can also be more than 2. So while in this particular example here, what we are encoding is pretty much a pairwise preference because we have 2 items and we are saying, okay, the user prefers the first item to the second one. In case we have a set which is greater than 2 and we allow the user to choose any number of items, then this becomes much more generic. This makes, in some sense, the life of the user a bit easier because, for example, if the user is undecided, if we are given 5 items and the user is undecided between 2 items, he can just say, okay, for me, these 2 items are equivalent, so I'm choosing both of them. So the way we are encoding this is we are encoding this with the set of choices. So for a given choice A, set A, we have a choice set C of A, but also a set of rejected items R of A. The idea is, again, to encode this concept of incomparability. So maybe we have 2 items that were selected both by the user, and the user is not able to either decide between the 2 because the user has implicitly multiple conflicting objectives, or because the user doesn't have enough knowledge to make a choice. So what we will assume when we learn from this type of data is actually that there are multiple conflicting objectives. So then we assume that everything which is in the choice set is belongs to a Pareto set. So here you have kind of a summary of what it means to be Pareto dominant, at least in this specific in the following slides. And for us, the set of non-dominated option is going to be the set where there exists, where we cannot find something in A which dominates the set X. Sorry, the item X. So all of this because when we are looking at the choice set, so C of A, this is the set, the non-dominated set in the strong Pareto sense for a certain vector U of a certain vector of function U, which describes what are the implicit objectives of our user. So maybe just to make it a bit more clear and going back to the emoji here. We have, in this example here, we have kind of 5 possible options, and for some reason, we are given the fact that somebody gave us told us that the true implicit objective that the user uses to evaluate these items are these 2. So then we have that, for example, this item here strictly dominates this one. But the set of non-dominated options is this one here, so this 3 cupcakes there. So what we are trying to learn is from observing this set of non-dominated options, we are trying to learn the underlying utility functions. So for the remainder of the talk, since I have very few minutes left, I'm just going to assume that the number of utilities is given. If you don't know it, which is often the case, what you can do is you can actually find it, and we showed in our paper that is actually quite reliable. You can find it with leave one out cross validation. This number of utility functions. However, let's assume that this is given. Then what we need to do is we need to encode in order to link these utilities with the observations, we need to encode this idea of non-dominated options. So this is done with these 2 kind of conditions, which I'm not really gonna discuss in detail, but just to give you an intuition. So the first condition, so maybe let's start with the second condition here, is simply saying that for each object, so if I take an object in my choices, so the object I've chosen, there is no better option in the set that I've chosen. So those are actually the choices I can make, which includes the incomparability. And then the first condition instead is telling me, okay, those are the best options. The options in C of A are the best option, actually. So for each option that I've rejected, there is at least one object in C of A which is not worse than this object in the rejected. So the way we actually encode this is we can either do this in an exact way, but then we are back to the issue that we mentioned before in the object preferences, or we can do this with a likelihood that accounts for the errors. And while again this formula is quite complicated, it looks quite complicated, is in the end exactly what I mentioned before. So the 2 conditions. So the green part of this formula is the condition that for each object in C of A there is no better option in C of A. So all the objects that are in there are incomparable. And the blue part instead is telling me that the options, so the objects that we have in C of A are actually better, or at least there is at least one object in C of A which is better than any of the objects that you can find in the rejected ones. And the advantage of using a kind of a soft version of the constraints that I mentioned before is that this allows for accounting for errors. So yeah, maybe let me skip this. And yeah, so then once we have this type of likelihood that I showed before, we can again fit a GP in kind of the standard way. However, we have still the same issue that we had in label preferences, where we don't have an analytical formulation for the posterior. So again, here we resort to variational inference. In this case, I'm pretty sure, well, for example, EP, we know that it works. However, we have observed that usually variational inference works better in barring all the possible issues of variational inference with the convergence, but that's another story. For prediction, the way we do it as you would do standard in a problem where you have computed your posterior variational inference. The nice thing about this, though, is that if you use Monte Carlo sampling from the posterior, from the predictive posterior, you can also assign probabilities to individual choice sets. So then you can, for example, use it to suggest what are better choice sets to the user. So one example here, and then I'm going to maybe close, is an example where, again, we used students and we asked them to evaluate a certain set. So in this case, the sets were sets of images of different ellipses. And they were asked to evaluate what is the best ellipse based on, and in this case, we gave them the objectives, based on two objectives. So the first one is small eccentricity, so they have to be close to a circular shape. And the second one is how much they are aligned with the Cartesian axis. So for example, this is not very aligned with the Cartesian axis, and well, also doesn't have the best eccentricity. So we repeated this task 160 times, and we generated a few choice sets. So an example of a choice set in this case is the student is given this set of images and selects the image number 6. So again, our data set are these choices. So a set of this type of instances. And for each ellipse, we use the pixel values of the image as features. And now what we want to learn is the implicit functions that drive these choices. So in this case, we use two latent dimensions because, well, in this case, it was given that there were two. And the way we evaluated this was with a 90-10 train test split, and we obtained an accuracy of 84. So maybe even besides the actual result, I think what's interesting is, again, to show an example of a prediction. So this is the, let me just make sure, yes. So this is the exact same example that I mentioned before. So we have the user was given these 3 images and selected number 6. And here we have the posterior, the estimated latent functions. So in this case, we have, this is the U1, the first latent function, and this is the second latent function. And for each of the ellipse, so for each of the items here, I'm plotting the value, so the posterior distribution of the latent function value. And you can see here that in this case, both of the estimated latent function are much higher for ellipse number 6 than for the other ones. This is another example instead where we have incomparability. So here we have 3 items again, 15, 18, and 21, and the user selected, the student selected 15 and 21. And in this case, the model actually, well, is actually consistent with that, because what we are seeing here is that, yes, for the latent function 1, the posterior of ellipse 21 is the highest one, but then for the latent function 2, the posterior of the ellipse 15 is the highest one. Okay, so again, in this case, our prediction would be actually 15 and 21. And what's interesting is that you can see that this role is really given by the 2 different latent functions. Okay. Yeah, so I think I'm gonna close now. And maybe just a quick recap. So what we have shown today is kind of three types of three ways of encoding preferences. One where the features are related to the object, another one where the features are related to the user, with the subject, and there are rankings. And a third one where we have kind of a more generalized way of encoding preferences, which is not either a binary pairwise comparison nor a ranking. So you can, we have shown for object, especially for object preferences and choice data, that you can use this inside Bayesian optimization pipelines. So I haven't shown it to you, but we have a few papers on that. So if you're interested in that, I can well give you the references. If you are interested in playing with the code again, I suggest you have a look at the prefgp Python package. There you will also find some notebooks that allow you to reproduce some of these examples. So if you want to play a bit with those, then yeah, you're welcome to do it. Okay, so I thank you for your attention, and I hope I didn't skip any questions because I cannot hear you, so I don't know if there were some questions in between, but questions are more than welcome now.
Yeah, thanks a lot, Dario. I think it's quite impressive to see how the model can actually capture like human preference towards like the learning choices.
Mm-hmm.
I'm wondering, I have a bit of a hard time imagining how that works in the Bayesian optimization context, because you have like a very finite number of choices you can make. So maybe if you could elaborate on maybe like a realistic case if you have one at hand in the like learning choices.
Yes. So in okay. So for the way for the moment we have used these models inside Bayesian optimization was then actually to rely on the latent function that will learn. Okay. So yes, it is true that you have a finite number of options that you can have. Okay, but you can still, for example, given a certain amount of given given a new set of items, well, actually, even better. You can try to suggest sets of items to the user that you know that are going to be maybe more preferable to the individual user. So maybe let me show you. I think I have something in here. Let me see if I have. What is it here? I wanted to see if I, no, but those are just comparisons. No, I don't have a, no, I didn't put it in the end. I thought I had an example, like a very simple example where this is shown. But no, one thing you can do for sure is to try to improve your knowledge on the latent functions with so by suggesting new comparisons. Okay, and then once you have that, the idea is okay, when you will need to predict whether what is the choice set that is going to be chosen by the user, then you're going to have a better model. Okay, so that's one thing we did. And the way you do this is, for example, by using, by considering this as, multi-objective Bayesian optimization problem. Okay, you have learned the GP with the choices, okay, but then you still have the posterior of the GP, and then you can use, for example, an acquisition function such as one that we use is the Pareto, so the ego with the Pareto front, or some type of choice, some type of Thompson sampling, which is specific with Pareto fronts, and then you can try to improve your model. Then
so maybe could you that what you want is to uncover the Pareto fronts. So what
yes.
you would recommend in a sense, like you give 3 choices to the user, but these 3 choices is the choice that will inform best, like how to learn the Pareto fronts. It's like you're not sure of the relation between two choices. So if you give it to the user, you get a lot of information from that new experiment.
Yes, I'm not sure I'm understanding correctly, but yes, and so it's the idea is to find what are sets of items that you can propose to the user in order to obtain the most out of this, right? And so to learn better the Pareto front. One thing actually you can even do is you can, and actually that is relatively cheap in the end, and something we have done is to propose, so once you find interesting items, so like you use an acquisition function, then you will obtain you use an acquisition function to obtain what are possible points, feature points that are interesting. Then you can actually generate the item from these features, and then you can show different combinations of these items too. Okay, so you're not really necessarily forced to show them the same set all the time. So once you have created the items, then you can kind of recombine them in different ways and propose them to the user if that's relatively cheap. So one example where this is used, for example, is in when we are we have kind of an application with a company where they make machine pieces. And for these machine pieces, what is costly is to actually produce the piece. Then to do the comparison, so to actually generate choice data is very cheap, right? So what we can do is we can generate a batch of, we can optimize the acquisition function maybe also with a batch acquisition function, and then this will give us a certain number of items that we can produce, and then we can generate all possible combinations. For example, instead of creating, we create 10 items. And then we generate all possible combination of set of 3 items, and then we give it to the user. So this automatically gives us back a lot of additional data, right? And I don't know if this was kind of the direction you were going here.
Yeah, I was only thinking of the second part. Is like given some choice, like you have a large number of choice, what is the most interesting experiment to put in front of the user? But what you explain makes sense. Like on top of it, you can also use your models to create new choices, and then you use your model a second time to create the best set of choices to put in front of the user to be most informative.
Yeah, I mean the idea is that I mean, ideally, you would want to get to a model where I mean, it's a bit contradictory there, but you would want to have something which almost always produces, generates kind of decisive choices from the user, but then since you are learning the Pareto font, probably you're also showing to the user while you are learning, you're showing a lot of incomparable stuff, right? So hopefully then eventually you will learn how to distinguish between these two. But if there is an intrinsic incomparability, then there is not much you can do there. You will learn the whole Pareto font there.
I'm afraid we're out of time. I don't know if someone has a burning question to ask, or otherwise we'll stop now.